Hello, I'm Dr. Ronan Connolly. We've just published an important new peer-reviewed paper in APJ, the Astrophysical Journal. In this paper, we're looking at changes in the energy coming from the sun, the total solar irradiance, or TSI for short, during the satellite era. That's from 1978 to present. Now, this is something that most people who've thought about it have assumed that it should be a fairly straightforward problem, but it is surprisingly challenging and controversial. In our new paper, we've discovered and shown that there were major problems with the main satellite composites that many scientists have been relying on. In this video, I'll dig into the details and summarize our key findings. It is quite a complex subject and it may get a bit technical in places, but I'll try to explain things as I go. So, if you're interested in learning more about what we know about the fascinating star that we call the Sun, then let's begin. In the early 1600s, with the invention of the telescope, Galileo Galilei and others began pointing the telescope at the sun. Of course, you shouldn't look directly at the sun through a telescope without a special filter. But if you shine the eyepiece of a telescope onto paper, it's possible to see features on the sun's surface. So Galileo and others, when they started doing that, they noticed dark spots would often appear on the surface of the sun and last several weeks before disappearing. Every day as the sun rotated around its axis, these sunspots would rotate with it. This was a shocking discovery. Previously, it had been assumed that the sun was a perfect sphere that never changed. So, while most of the early astronomers used their telescopes for studying the night sky, as astronomers do today, a few would also use their telescope in the daytime to draw sketches of the sunspots. One of those observers was the German astronomer Heinrich Schwab. In the 1840s, he kept a continuous record of sunspots lasting 17 years. He discovered at the end that the number of sunspots seemed to follow a distinct cycle, lasting, he estimated, about 10 years. He found after months with no sunspots, the sunspots would start to increase every year for several years in a row, reach a maximum, and then for the next few years, the sunspot numbers would decrease all the way back to zero. A Swiss astronomer called Rudolf Wolf was so excited by Schwab's discovery of a sunspot cycle that he decided to collect all of the sunspot observations he could find to see if it was true. He discovered that yes, there is a cycle. It wasn't a strict cycle in that the length can change from 8 years up to 14 years, but it was Schwab was right, and the average is about 11 years. Now, we now usually describe solar activity in terms of these sunspot cycles. They're so well defined. We call them solar cycles, starting with solar cycle 1 in the 1750s. Currently, we're approaching the maximum of solar cycle 25. So, the sun shows changes in sunspot activity, but does the actual energy output from the sun also change over time? And if so, could it contribute to climate change? Samuel Langley was an aviation pioneer. He was one of the inventors developing the first aeroplanes at the end of the 19th century, early 20th century. So he'd invented some of the first unpiloted planes in the late 19th century, and he was also involved in the race for developing the first manned planes. And that race was eventually won by engineers like the Brazilian Santos Dumont, the North American Wright brothers. But Langley's contributions were so significant that the US's first aeronautic laboratory was named after him, and that later became what's now NASA's Langley Research Center in Virginia. Langley was also an astronomer, and he was very interested in the possibility that the sun's energy might change over time. And he wondered whether, if that was happening, it might contribute to climate change. In an important paper published in APJ in 1904, he called on scientists to begin systematically trying to monitor the solar radiation reaching the Earth. Now, he warned, however, that any attempts to do so would be imperfect. He realized that measuring the sun's energy from ground was not a direct measurement of the energy that reached the Earth's atmosphere. Instead, it was just whatever hadn't been absorbed or reflected away by the atmosphere on the way down. Still, at the time, the idea of flying up high enough to leave the Earth's atmosphere was still complete science fiction. So Langley decided it was the best they could do for the time being. In 1890, he had founded the Smithsonian Astrophysical Observatory, SAO. So he organized a measurement program at the SAO that would continue until 1962. Years after the SAO program had ended, a scientist called Doug Hoyt tried to see if he could find any trends in the data. Unfortunately, he discovered Langley's concerns had been correct. It turns out that the variations in the SAO measurements seem to have been dominated by changes in local weather, observing conditions, differences between the instruments used for each set of observations. So it seems Langley was right. If we want to properly monitor the changes in the sun's energy, we need to do so from above the Earth's atmosphere. Now, fortunately, by 1979, that was no longer science fiction. We are now capable of launching satellites. In fact, Doug was on the science team in charge of the first satellite mission to continuously monitor the sun from space, Nimbus 7. And in 1980, the second satellite mission was also launched for TSI. The first ACRIM instrument was launched on NASA's SMM satellite. By this stage, we had more than 350 years of sunspot observations. So one of the first questions that scientists wanted to answer was, is there a relationship between sunspots and TSI? And if so, what is it? People had been speculating on different possibilities. In 1976, Jack Eddy had pointed out in the journal Science that in the mid-1600s, there was a period when sunspots had almost completely disappeared for about 70 years. Climate scientists had noticed that was also a period of global cooling, what we now call the Little Ice Age. He suggested that maybe that wasn't a coincidence. But without direct TSI measurements, we couldn't know. So roughly, there were three competing hypotheses on the relationship between sunspot activity and TSI. One, the sunspots are dark features, so maybe when sunspots are there, that reduces the amount of TSI leaving the sun. Two, on the other hand, you could have when sunspot numbers increase, sun seems to become more active, more solar flares, more solar eruptions. So maybe less sunspot activity means less TSI and global cooling. Or maybe TSI behaves independently of the changes in sunspot activity. As we'll discover, it turns out that all three of those hypotheses were partly right and partly wrong. In this graph where I see here the first year of the ACRIM 1 satellite measurements on the top here. And on the bottom, we have the daily sunspot numbers at the same time. And you notice that when a sunspot group, a large sunspot group passes by and you get a high sunspot numbers, that's often associated with a sudden drop in TSI of a couple of watts per meter squared. You can see I've shown three examples here. So if we could look at this is a graph here, you can see that this is TSI and this is the number of sunspots. And you can see that on average, the higher the sunspot numbers, the lower the TSI. There's a relationship there over the course of 1 year. But if we look at 10 years of data, this is the entire ACRIM 1 satellite mission. It lasted nearly 10 years. And notice how we're seeing that as, as the sunspot numbers reach the solar minimum, TSI also decreases to a minimum and then it increases again. So when we look, instead of looking at just 1 year, if we look at 10 years, we find that the relationship between TSI and sunspot numbers is actually reversed. You now get an increase in TSI with increasing sunspot numbers. So we seem to have stumbled onto a scientific paradox. 1 year's data proves hypothesis 1, but 10 years' data proves the opposite hypothesis. What was going on? As often happens in science, things are more complicated than we expect. Turns out that when sunspot activity increases, it's not just sunspots that are increasing. Bright features on the sun called faculae and plages also become more common. They are harder to see on the sun than sunspots. It is easier to spot a dark patch on a bright object like the sun than to spot a bright object on a bright object, if you know what I mean. So we don't have as much data on faculae as we do on the sunspots. But these two NASA videos are based on data from NASA's SDO spacecraft. They show 1 month's observation of the sun near a solar maximum in April 2014. We can see the sunspots clearly in the video on the left, which is based on HMI magnetic readings. On the video on the right uses a 1700 angstrom filter, which makes it easier to see the faculae. Notice how, with the filter, around each dark sunspot there are large bright regions, faculae. Also notice that there's networks of bright features across the sun's surface that aren't as obvious from the video or associated with sunspots. This explains why over the course of a solar cycle, sunspot activity is correlated to TSI. That is, when sunspot activity increases, faculae activity also increases. And these bright faculae increase TSI more than the dark spots decrease it. But does that coincidental relationship between sunspot activity, faculae, and TSI remain the same over multiple solar cycles? That's been a controversial debate that's been ongoing since the late 1990s. Here are the 4 main TSI missions launched between 1978 and the early 1990s. Do you notice how none of these records spans more than 2 solar cycles? That means if you want to study the intercycle changes, you need to combine multiple records into a single composite record. The ACRIM team, led by Dr. Dick Wilson, was the first group to develop a TSI satellite composite record. They prioritized their own ACRIM satellites since these were high quality instruments designed solely for measuring TSI. They also used Nimbus 7 data to fill in missing gaps. The ACRIM team updated their composite multiple times during the 90s and early 2000s. The third and final ACRIM satellite was launched in 2000 and it ran up to early 2013. In this graph, I'm plotting the final ACRIM composite after from 1978 to 2013. Now we're looking at 3 solar minima. That's how long we're doing, and you can see nearly 4 solar maxima. Notice how every solar minimum is always the exact same value, 0. You can't have less than 0 sunspots. But the TSI in each minimum is different. Also, we can see that the TSI during the solar maxima shows different behavior, slightly different behavior than you see for the sunspot numbers. That is, on short time scales, sunspots decrease TSI. Over the course of a solar cycle, TSI rises and falls in tandem with sunspot numbers. But over longer time scales, TSI can also change between solar cycles. This had 2 immediate consequences. First, it meant that relying on sunspot numbers was not good enough for working out how TSI had changed over the centuries. So, according to the ACRIM composite, it's true that there is a linear relationship between sunspot numbers and TSI. But the key point here is that the changes in monthly sunspot numbers can only explain 47% of the monthly TSI changes. So, some other aspects of TSI variability are not being captured by the sunspot record. A second consequence was that the ACRIM composite showed an increase in TSI between the solar minimum in the mid 1980s and the next solar minimum in the mid 1990s. The 1980s and 1990s were a period of global warming, and the UN and others had been claiming that global warming was due to increasing greenhouse gases. But the ACRIM composite suggested that at least some of that global warming might actually be due to increasing TSI. Then, later in the early 21st century, global temperatures famously entered a temperature hiatus, where temperatures neither rose nor fell for more than 15 years. And that was a period when, coincidentally, the ACRIM composite suggested a slight decrease in TSI. Was this just a coincidence, or did it suggest that maybe climate scientists had been underestimating the sun's role in recent climate change? Starting in the late 1990s, 2 scientists, Professor Klaus Froelich and Dr. Judith Lean, decided they didn't like the ACRIM results. They decided they would develop their own rival TSI composite. Professor Froelich was the director of the PMOD observatory in Davos, Switzerland, so their composite came to be known as the PMOD composite. In an interview for a NASA website in 2003, Dr. Lean explained one of the motivations for them to develop the PMOD composite was because they were worried that the ACRIM results might make people think that global warming could have a natural explanation, and that might interfere with international greenhouse gas policies. So they decided that each of the satellite records used by ACRIM needed to be adjusted. Their adjustments were different for each satellite. But what was the net effect of PMOD's various adjustments and data choices? Here is the PMOD satellite record. If you remember, for the ACRIM composite, we were finding a lot of variation in TSI between each solar minimum, but now that's all gone. It's almost exactly the same for each minimum, exact same as sunspot numbers. Also, we can see that a lot of the variability in the sunspot in TSI in the sunspot maxima has also been removed. We now have almost exactly the same for both maxima and minima. As a result, you can see here that we have an almost exact linear relationship between the sunspot numbers, and TSI over the entire satellite record. And you can see that the sunspot numbers can explain roughly 58% of the monthly TSI changes. That figure is even greater for the yearly values, which we discuss in the paper. The PMOD composite rapidly became popular with researchers who think TSI can't explain any recent warming. And because of that popularity, many other scientists who were unfamiliar with the details started assuming PMOD was the best one, simply because everyone else seemed to be using it. But today, a lot of the scientific literature you'll see assumes PMOD is correct. But is PMOD a more reliable composite than ACRIM? In 2008, Professor Nicola Scaffetta of the ACRIM team reached out to Doug Hoyt, the lead scientist at Nimbus 7, to ask him what they thought of Froelich and Lean's adjustments to their data. You might remember Doug was also that scientist I mentioned earlier who analysed Langley's solar constant data in that 1979 paper. He completely disagreed with the PMOD's adjustments to Nimbus 7. As well as finding the adjustments to be unjustified, he argued they were physically implausible. The ACRIM team also disagreed with the PMOD adjustments. As we discuss in the paper, the debates between ACRIM and PMOD over how TSI changed between those two solar minima in the 1980s and 90s have continued for decades, and they're still ongoing. But in our new paper, we show there's also controversy over the TSI trends since then. With the ACRIM PMOD debate, the main problem is a shortage of satellite data in the 1980s and early 90s. But since 1996, there have been multiple satellite missions available, and many of these have lasted more than one solar cycle. So now the challenge is deciding which satellite missions are the most reliable. These are the 5 TSI records launched since 1996 that have more than a few years of data. And you can see 3 of them are still active, and ACRIM 3 and Source each had more than one solar cycle's worth of data, 13 years, 17 years. And that at any one point there was at least 2 and up to 3 or 4 satellite missions available at the same time. And that initially sounds like a great thing, except that each of the missions shows a slightly different behavior at over the course of their record. For example, do you notice the way that this blue ACRIM 3 curve is at the top of above the green and red at the beginning of the ACRIM 3 mission, but by the end of the ACRIM 3 mission, it's down below the other 2 graphs. As another example, you can see that the source TIM, the red line, is consistently below the green and blue, but by the end of the source mission, it had risen to being the highest of the 3. So what that means is that source TIM is showing a slight increase relative to PMO6 over time, and ACRIM 3 is showing a slight decrease relative to the others over time. So this is figure 2 from our paper, and you can see on the left-hand side we are showing several composites that have been published in the literature, but they haven't been updated in years. And the top one is the ACRIM composite we discussed, and this is Froelich and Lean's, the last version of Froelich and Lean's PMOD composite. We can see there are also 4 different composites that are still active, and they're regularly or intermittently being updated to present. So these, at the moment, before our paper, these four are the most up to date satellite TSI composites. But we realize there are many different scientifically plausible ways that you could combine the satellite data into a complete composite for the satellite era. In the paper, we update another 7 of the discontinued composites, and we also develop an additional 10 new composites that have never been that apparently have never been attempted before. That brings us to a total of 21 different composites. 21 is a lot, however. So we also use statistical techniques to cluster each of the composites into 6 similar groups, and then we study the averages of these groups. And there we can see, I've also indicated here with blue dashed lines, those are the times, approximate times of the solar minima, and the red lines indicate the solar maxima. We can see Group A looks pretty much like the PMOD composite. There's almost no changes in either minima or maxima. And that's not too surprising, because this is the group that contains all of the composites using the Froelic's PMOD adjustments. But the other 5 groups show considerable variability in especially the minima, but also in the maxima. Now, the groups B and C, they're updates to the ACRIM composite. The ACRIM composite, as we saw, ended in 2013. So to update it, you need data just from 2013 on. So these ones are different combinations of using the available satellites for the data after 2013. These estimates, groups D to F, they use ACRIM data for the earlier parts, but the ACRIM composites, but they will they'll prioritize the most recent satellite missions. Now, what we can just quickly seeing that the key bit to look at for us is the changes in the minima. So the ACRIM ones, they show an increase between the first 2, as we discussed, but they also show a sharp decrease between the minima in the 90s and the early 2000s. That is not shown by the others. And that's mainly because ACRIM composite used ACRIM 3 for this period from 2000 to 2013, which, if you recall, was a bit of an outlier. It showed a greater decrease than any of the other missions that are available. So that's why with these ones we find that there's actually a slight increase between the 90s and the early 2000s. And for D and E, we find a slight decrease for the most in the most recent solar minimum, but Group F shows an increase over all 4 of the solar minima in the satellite era. So, which one of our new TSI composites is correct? Well, in my opinion, I find composite A the least plausible, because it relies on dodgy data adjustments that seem to have been politically motivated rather than scientifically justified. That's my opinion. We give details in the paper of other problems with it. Of the remaining composites, because the ACRIM 3 satellite data seems to be an outlier among the most recent missions, I personally think that composites D, E, and F are probably more likely to be correct. But maybe ACRIM 3 was correct. I don't know. After those remaining three composites, I think they all are plausible. But it is worth noting that both D and E partially used the late Professor Froelic's PMO6 satellite mission on the SOHO spacecraft. In addition to the PMOD adjustments he applied to the other satellite missions, Froelich also applied adjustments to his own satellite record. He sadly passed away in 2019, so he can no longer comment. But I must admit, given what he did for his adjustments to the other records, I'm frankly a bit wary of his adjustments to his own data. So maybe Composite F is the most reliable. If that's true, then it means we'll have to completely revisit what we know about TSI changes, not just in the satellite era, but over the past few centuries, because all of the TSI reconstructions, and there's a lot of them that are currently assuming that sunspot numbers are capturing much of the TSI variability. They're based on assuming that this is accurate, the group A is accurate. But if F is correct, then you can see, just notice this divergence between the sunspot numbers and TSI over time. That suggests that sunspot numbers are missing out on key intercycle changes in TSI. And the same applies for groups B, C, D, and E as well. So it is only if group A is correct that the sunspot numbers are a good proxy for TSI. But in the end, we don't know. So we've offered all of the data sets to the scientific community so that they can investigate for themselves. So that's the end of our long journey from Galileo to today. If you like this video, please like, subscribe, and share. And if you want to learn more, the paper is available in the Astrophysical Journal, and you're welcome to download the data. And you can find out more about our other research at the series website. So thanks for staying with me to the end, and hope to see you in later videos.